So in this first part of this required pre-lecture video, we're going to discuss the idea of power. So we've learned a lot about work and energy so far, and we're going to now talk about this related term, power, which is defined to be the rate of energy transfer. So dE dt, the time rate change of the energy. So it's related to energy, but it's not equal to energy. It's the rate of energy transfer and so the power depends on time, which so far in our entire discussion of work and energy, you'll note that nothing has depended on time so far. So there's just a quantity of energy, say in joules, but there's nothing about the rate at which that energy is being transferred or transformed. And so power takes that into account. So the unit of power would be the unit of energy divided by the unit of time. So it would be a joule per second, which is defined to be a watt. And you're familiar with the unit of watts, since that's what we commonly use for electrical appliances for their power rating. So for example, an old-fashioned incandescent bulb that's 100 watts would then use 100 joules of energy for every second that it's on. So the power rating, if it's never on, then it doesn't use any energy, but it tells you for how long it's on, how much energy it would use. So the power then is energy divided by time. So we can talk about then the average power, which is going to be equal to the energy transferred divided by the time interval over which that energy transferred occurred. So for example, sometimes if the energy is transferred via work, then the average power would be equal to the work done divided by the time interval over which that work was done. So remember, the definition of work involves the force applied and the distance that it traveled, but nothing about the time in which it took to do that. And so if it took a small amount of time to, say, move a box across a table, that would be more power. If it took a longer time, you moved it very slowly across the table, you might have the same energy transferred in both cases, but the power would be different. Okay, so let's do an example, which I've already written out to help save time in the video. So let's say we have a person that's going to push a 10 kilogram block up two different frictionless ramps, both at a constant speed. So the constant speed tells us two things. First, that the net force is zero, there's no acceleration, and that there's no change in the kinetic energy. Say that it takes 5 seconds to push block up the ramp A, and 10 seconds to push the block up ramp B. So the question then is to find the power dissipated in each case. So if we want to do this, we can use then our previous example of the case where energy transfer is from work done, and there'd be work done on this box by the force F, which then would be the power, the energy transferred, and the time interval over which that was applied is given in the problem. So we can say work done divided by the time interval. So we're going to use that the average power is equal to the work done over the time. And so then we need to use our definition of work, which is that the work is going to be equal to the force applied for a constant force, remember our simplification for the work done, dotted into the displacement S, which is going to be up the ramp. So let's go ahead and just draw a ramp that has some angle theta and some height h, and then some displacement S, which is the hypotenuse of that triangle. So in this situation, then, we can figure out what S is in terms of h and theta, since those are values that have been given to us in our problem. So from this, we can say that the sine of theta is equal to h over s. And so then that tells us that s is going to be equal to h divided by sine theta. So the height of the ramp divided by sine theta. Now the other thing that we can do is that we can draw our free body diagram, because we don't know anything about the force in terms of h and theta, h or theta, I should say. And so we can use the idea that there's a constant speed, and we can go back to what we learned previously about net forces. So we have the normal force pointing up, we have our force F that is pointing up the ramp, and then we would have our weight downward, so mg. Now, if we look at this, we know that the sum of forces along the ramp, which I'll call the x direction, the sum of forces along x is going to be equal to 0. So the magnitude of the force equals the component of the weight down the ramp. Right? This component of the weight. So remember this bit about drawing the components for this weight. And you should know and be comfortable with from our previous material that this is going to be equal to mg times the sine of theta. So from a quick review here of our Newton's second law application, we should be able to see that the magnitude of the force is equal to mg times sine theta. And that's again because of constant speed. If you weren't given that information, you couldn't make this determination. All right, so now we have to look at the scalar product here, and we see that F and S are parallel to each other and in the same direction. So this is going to simplify to that the work, which is the scalar product of F dotted into the displacement, is simply going to be equal to the magnitude of F times the magnitude of S, which we have now solved for. So if we plug these in, we see that we get mg times the sine of theta divided by the sine of theta times h. So the sine of thetas cancel, and in the case of this general ramp with some angle theta and height h, the only thing that ends up mattering is the height and not the angle. So theta does not matter. So if we have this result, mgh, for the work done in both cases, then we can see that it does not matter about the angle of the ramp. It's the same work for both cases. And so all that's going to matter for our average power is going to be the time. So it's going to be equal to mgh divided by the time. And so for ramp A, where we were told it was 5 seconds, then it's going to be equal to mgh. And if we look here, we have 10 kilograms. And then for the height was 1 meter. So we're going to have here 10 kilograms times 9.8 meters per second squared times 1 meter over 5 seconds. And in case B, it would be divided by 10 seconds. So here we're going to end up with 98 divided by 5, and that would be our watts. And for case B, we're going to end up with 98 divided by 10 watts. And then we can see that the shorter time is going to be a bigger power. If the time had been the same, if they had been taken the same time to push them up, then the power dissipated in each case would be the same because they reached the same final height in the same amount of time. So the same amount of work was done in the same amount of time. The last part of our discussion of power is going to involve the idea of a kilowatt hour. So a simple question would be, what is a kilowatt hour a unit of? And a kilowatt hour is not an SI unit, but it's one that's commonly used, which is why I mention it. A kilowatt hour would be equal to a kilowatt multiplied by an hour, which is going to be equal to power multiplied by time. And so then what you should realize by now is that that would be equal to energy. So kilowatt hour is how, when you're in your house and you're trying to make sense of your electric bill, what you get billed for are how much energy you've used, how much electric energy you've used. And they bill you in kilowatt hours. And so you can look at a given appliance, see its kilowatt rating, and then multiply by how many hours a month, say you use it, and that would give you your kilowatt hours. All right, that concludes our discussion of power. We're going to now move on to the second part of the video, which is going to discuss conservation of energy.